to occupy certain seats or certain distance from this, correct? Right? The moment I open the door, the moment I stop my lecture, okay, there is no influence of me on you. Therefore, once you go out of this room, you can take continuous energies. Somebody wants to go to the hostel, somebody wants to go to movie, somebody wants to go to shopping mall, somebody wants to go outside the campus. You are taking continuous energies while any. So you are not influenced by the person who is taking a lecture here. Because for the same thing happened in the energy quantization, that when the electron is near to nucleus, it wants to occupy certain energy states. It cannot take continuously. You know continuous and discrete, right? Say yes or no. Right. Continuous means there is no separation between the energy. Okay. So discrete means there is a separation between the two energy states. The center is forbidden. Okay. So if electron is close to the nucleus, it will occupy a particular energy state zone. But when the electron is far away from the nucleus, so the nucleus influence on the electron is not that significant. Therefore, the electron will get continuous states. And the electron which occupy in the first excited state or the near to the nucleus, these states are called bound. Because electron is bound by the nucleus. Here you are bound by my presence. Once you go out of this room, you are unbound. You are continuous. Think of like that. The similar way, you have a wall and this side. You throw a ball, what will happen? It will make back and forth, right? So it doesn't, it will make back and forth. It will do this kind of motion. Am I right? Say yes or no. So it means that it is bound by these walls. Suppose if the wall is not there, what will happen? So it will take continuous energies. To think like that. Because it is not bound by anything. The moment you trap a particle inside the box, what is called particle in a box, okay, it is bound to take a certain energy states. That's what it's called energy quantization. Now do you learn? Say yes or no. This is a very, very fundamental thing that you should know. So when you say what is the difference between the classical and quantum, this is how one should define. And there is a Schrodinger equation. It's a time independent. You don't bother about too much mathematics. Just I will try to give you a physical intuition. Okay. So the wave function which determines the probability of finding a particle. When you throw something here, right? Okay. This ball goes with a different probabilities on its way. Correct? Say yes or no. So when you are doing this, the probability of finding. See. And here is minimum. Right? Over the time also. Because very less time the particle is spending at the interface. As it's bouncing back. And you are having maximum probability in between. So when you try to measure the particle behavior or the particle probability, that's how it takes time. Once you throw the ball, okay, let's say that you are measuring at the center. Okay, when the heat can come back, you catch. What will happen? All the information is coming to collapse there. Because you found the particle. Okay. Okay, your wave function is a function of space as well as the time. That's more important. So in the intuitive way, you can think of like this. When you are going on to the top, as I said, you will have a continuous. When you are taking the continuous things, there is no discrete. Okay, so when you come back, when you see the classical world, this is this thing. When you see the quantum world, it's like a steps. So you are not how to play. We have to what is called configuration. Okay. This is like discrete steps. That's what it's called. It's energy quantization. So you are going lower energy to the higher. Okay, this is just to convince you that I brought this down. The next one is the correspondence principle. Okay. Do you have this principle? Say yes or no. Okay. Let us say that this I will give you another example. That have you observed that when you are close to, you are more concentrated. Am I right? Say yes sir. When you are less concentrated, if you are far away from the teacher. Correct? Correct? You are a superposition of more concentration, less concentration in video. Why that is so? The reason is simple. Of course, Sri is watching you. That is one thing. It's simple. Of course, Sri is watching you. That is one thing. Clear? So the electron also feels the same. Electron, when it is close to the nucleus, it feels the more equivalent sonics. So that means the nuclear, in some sense, equivalent sonics. So that means the nuclear, in some sense, is attracted to any option. But when you are little far away, like a center way, what you are going to do is that, oh, if somebody is really interesting, you will focus. If it is not interesting, you don't focus. But I'm not sure at the back bench is what they're doing now. Our next. So the same place. It's also nuclear, also not sure. So your only I can say your front row is a quantized. Next is partially quantized. Maybe there's no quantization there. It depends on you. Think like that. Okay. The intermediate region. Okay. What do you see? Because there's no a particular quantity. Number gets more and more. What will happen is that there is a close spacing between the energy states. It's like almost like you feel continuous. There is no state. Okay. So therefore, you don't. The electron will not feel the effect of nucleus. Or you don't feel backbenchers do not feel the influence of teacher. So it is like no matter whether they are out of the room or inside the room. It's a classic. More front people are more close to quantum. So if you want to learn the quantum, basically, right from where that's not possible. It's possible. The same thing happens in academics as possible. It's that every electron can sit close to the nucleus. It has a certain number of electrons it cannot. Let's move to the next. Okay, this is how it is designed. So this principle at the front you have a fully quantized system. At the highest you must be close to the classic system. In the middle you have a mixture of both. Okay, that's what it's done. That way connect the quantum world and the cluster world. Quantization. Okay, that's very important. Now this is what I said. Do you know the Pauli's exclusive principle? You can't measure simultaneously. Always you are limited by some limitation. That's what it is called. What is uncertainty? So you are not certain of something yet. So that means that you are not so sure. And you are not so sure about the momentum. So how you are sending a water, reducing the uncertainty of the water molecule in this direction. That means what you are going to have, your uniform distribution of the velocities. Now you try to squeeze the velocity distribution gets damaged. Okay, which means that in the previous case, you have a good accuracy in moment. But the moment you get squeezed, you are getting a good accuracy in position, but you are not getting a good accuracy in momentum. This is what it is a application of the uncertainty principle. If you want to know high precision in position, so you have to compromise on the momentum. But if you want to know high precision in moment. Okay, these are the two things which it's not possible. That is what Hyderabad considered. This is the physics side. So what? So what is that physical mean? How many of you pair the time? It is making a wave nature, a dual nature. Okay, if you see at a fixed, the striker, you see the striker, right? So that is like a particle. But if you see, if you let it freely go, the zero will be at the ends, boundary. Okay, so it means that it makes a wave function. It makes the wave function. Are you able to follow what I'm saying? So it makes the wave function at different positions. Okay? It is first verified by this. When it can behave like a wave function occurs, you win out. You are afraid about. No, it's the same bottom. It's the same point. Afraid of the table. Do you get that? Okay. Huh? What do you get? What do you get? Right? So all the time, it is a slope position of. So all the time, it is a slope position of. Can we have? Can we have? It's okay. Can we tail also? It's okay. Can we tail also? When when the head or tail. Okay, that is the essential difference between the classic. So in the previous case, you see there, either that is zero, there is no change in it. But when you just imagine, the moment n is becoming a 1, yeah, no, no, no. Stupid question also no problem. Question should be asked. Do you understand everything? Which I don't understand. How come you understand everything? Please. Yeah. Okay, anyway, I will be here. So, her question was, does it have any applications in transportation or the traffic and all the thing you can monitor and all the things? Only thing I can give is that it has applications, and obviously I'm not working on that. But briefly, I can tell you is that the position and the because now, as you may know, that the AI and all of the things they are trying to develop a autopilot, which means no driver cars, so that if you recognize with a quite a lot of data, that you can even sense where the accident could have happened or you can avoid it. So that kind of application might have it. Because of it is all because of you can precisely tell you the positions. So that's only I can say. So you can prevent our human life. It has to be generated from the same. Program has to be generated from the same. When the program from the generation is data also. No matter how much, you go to generate your local. So that after one done. Only non can go ahead. Right. Yes. Please ask. Students, yes. Right. Right. So that's a good question. Yes. The question one no right. Mike and the search. So you want mic? Okay. So actually the question was the measurement problem. So as I said, when you rotate the coin, right? So always you will have a superposition of either 0 or 1 or the head or tails. If you want to know the outcome, okay, before you measure, the system is quantum. Okay, but you have to know the outcome of the system, what is about. The outcome is the stopping is a measurement. Once you stop, then you have to be a 100% probability that either it has to be a tail or the heads. Okay, but once you stop, that means you collapse the wave function. So then it is collapsed either to the head 100% or tails. Then only you will know the information. That is at one point. Again, if you leave it and it will keep rotating, if you do the other time, you may get the other one. This is like this. It is not at one time then sir, what is the then classical and quantum? So you're saying that 100% you're getting X, then where is the quantum here? Before that measurement is basically you're disturbing the quantum system to know the outcome. So you disturb the quantum system, then you know the outcome. That's it. Thank you so much, sir, for amazing and inspiring speech of your on integration. It should be space. Knowledge is that. Keep practicing. Practice, sir. Okay. Good question. What is practice? You don't know what he means. So, okay, the question online it has come. How to use practice knowledge, sir? I don't know what does it mean the question, but one thing I can say. Please listen. 2 minutes. I'll leave you. Brother. So, hello. So, knowledge, what you read in the book, it's basically cognitive. And you learn by concept and all anything. But when you do the experiments,